now.
Okay, so go ahead and start then, or?
No, first I'm just going to say hello to the online people. I don't right now know how many people are online, but whatever. Sorry, we don't want the echo, so don't, if you can actually listen in, the live people here, you can go to the website. If you just go on YouTube and type in OnNeuro, you can find the page. And then you can type questions and comments into the comments, the chat box on that site, but don't play the audio because then we'll have a horrible feedback loop with echoes. In terms of how the format of this works, AJ will give a 15 minutes or so quick presentation, and then we'll have an extended discussion at the end. If you have questions or comments, online people, you can just type into the chat box and we'll get to you at the end. People here live in the room, you can raise your hand and Molly will appropriately interrupt when she deems is a good time. Also be mindful of tapping on the table because we have a microphone here. It's a brand new conference microphone, so you don't have to have a mic or anything. The microphone should pick up everybody equally in the room when you choose to talk. And then at the end of the presentation, we don't have to do the raising the hand thing. You can just pop in and ask questions and chat with AJ whenever.
Okay, but for our online listeners, especially those who are joining us for the first time, we want to welcome you to OnNeuro. OnNeuro is an online neuroscience and psychology conference. We meet once a month to discuss current research in the fields of neuroscience and psychology. And now, for the first time in history, OnNeuro welcomes our live audience. In collaboration with the Center for Cognitive and Behavioral Brain Imaging Student Group, our audience will be sharing combined worlds of online and in-person. So thank you all for coming. This month we have Dr. Andrew A.J. Collegio from George Washington University. AJ, welcome. Could you please tell us a little bit about yourself and your work?
Sure. So, hi everyone. Thanks for having me here today, and thanks to Paul, Molly, CCBBI, and OnNeuro for putting this together. I am a former graduate student. I recently graduated from Dr. Shara Shamstein's lab at George Washington University. I'm now still working as a researcher in Sarah's lab, and my work basically investigates how attention is constrained to objects and to different types of information in the visual world. So basically, when you're looking at scenes or you're walking through your world, what is it in your visual field that attracts your attention? How is it that you switch your attention between different locations or between different objects? And what types of information really change where your attention is directed? And so I'll be talking about some of that work today. The work I'll be talking about was recently accepted at a journal called Nature Human Behavior, and we're really excited about that. And this work investigated how attention to objects is affected by your prior knowledge about object identity and also about your own prior real-world knowledge about how large or small those objects are in the real world. And so that's the work I'll be talking about today, and I'm excited to share it with all of you.
Awesome.
Awesome. Thanks very much.
We're excited to hear about it.
Okay, so I will just jump right in.
So yeah, let me just switch over the screen and you can go ahead and start. For anyone who's online, since this is a new technical setup, please type in the chat whether the audio and video are okay, because I can't easily test that out. Room audio is better quality, but okay, thank you very much.
Before we begin, does anyone have any questions? Anyone online? Okay.
All right, take it away, AJ.
All right, sounds great. So to start, for a moment, I'd like you to just transport yourself here to this alleyway, this image of an alleyway where you see a cat and a man. And while we know that a cat is actually much smaller than a man, they're actually, in this image, surprisingly, roughly the same physical size as they appear on your eyeball or on your retina. And despite the fact that they appear to be roughly the same size, you have prior knowledge that the cat is much smaller than the man, and this arises due to multiple factors in this image, including depth. You can see that the man is further back than the cat. as well as a principle called size constancy. So basically this idea that objects that you know to be a certain size are usually going to be the same size in the real world. They don't typically change sizes. And basically this enables you to infer that this isn't really just a giant cat. It's probably the same size as a typical cat that you might encounter in the real world. And we were interested in whether this knowledge about object size might influence how you attend to different information, and specifically different objects in this scene. So how does this knowledge about object size shape how you engage with a scene like the one that you see before you? Given that size as it appears on your retina or as it appears on your eyeball is often inconsistent with the actual sizes of objects in the world. And this line of questioning that we pursued in this project was spurred by several studies, including recent work on how attention and how perception is affected by object size. And some of this work was conducted by Kunkel and Oliva in 2012. This was one of the main motivating factors for this study. And what Kunkel and Oliva showed here was basically that images and objects like this bulldozer and this binder clip are actually mapped in visual space in the brain, in the cortical space, according to their real-world object size. So basically what this means is that large objects like this bulldozer are actually mapped on visual cortical space on the medial side of the brain, so basically in this blue region, while smaller objects like this binder clip are represented or mapped in visual space on more lateral regions in visual cortex, which is represented in orange. And so this is interesting because what this is showing is that prior knowledge about object size, even though all of these objects images were shown at the exact same size on the computer screen when they were presented to participants, despite the fact that they were all the same size, participants had this real-world knowledge about objects, and that real-world size affected basically where these images were being represented in terms of visual space in the brain. And so this is really interesting, and it might also potentially have a behavioral effect. And so this was basically one of the main inspirations for pursuing, does this cortical mapping have a behavioral consequence, and specifically an attentional consequence? And we get a hint that it might. In particular, from other previous work, for instance, work by Castiello and Umilza in 1989, and what they showed in this study was that essentially in an attentional task where what they did was to present objects, either a small object like the small square you see on top, or a large object like the larger square you see on the bottom, as what's called an intentional cue. Basically, this object was directing your attention to a specific location. And then they presented participants with a target that was either in the small object or in the large object. And what they showed was that when participants were attending to a target that was presented within the smaller object, they were actually much faster at detecting that target, at finding that target, and responding to it, than they were when they were responding to a target within a larger object. And so this is basically a size effect, that if you're cued to a location that's a larger space, you're slower at attending to information within that larger space. And they went on to demonstrate further that this is also because essentially attention is more focused within a smaller region than it is within a larger region. In a larger region, attention is more diffuse. Essentially, there's more space to attend to, there's more area where a possible target could occur, and so there's more diffuse attention that slows target detection down. But you can see that these objects are not actually the same size. They do differ in terms of how large they physically are. And so what we were interested in was specifically whether attention is constrained not just by retinal or real object size, like real physical object size, but also by your inferences of real-world object size. So how large are the objects in the real world? So to illustrate this more clearly, if I can draw your attention back to the previous example of the cat and the man, if attention is operating solely according to the physical retinal size of the object, so how large the objects physically are, And essentially, there should be no difference in terms of how quick attention is allocated within those objects, because they're literally the same size, the same physical size. According to the work by Castillo and Umilta, because they're the same size, attention should operate at the same speed across these objects. However, if attention is actually operating according to your inferred knowledge of object size, so how large the objects are in terms of physical space, in terms of your knowledge of these objects, then what should be going on is that essentially attention should be slowed within the object that you know to be larger, because that object has more physical space in terms of your mental representation. And so what you should see is that response times to and within these larger objects, for instance in the man, should be much slower than in the smaller object, such as the cat. And this is demonstrated in this figure here. You can see, according to the real-world objects, in the yellow you can see that would be a predicted effect for a large object, and that would be much slower than in the predicted effect for the smaller objects, such as the cat.
Okay, can I ask about the image quality? Like,
sure.
The cat is sharper and the guy is blurry. Does that have anything to do with it? Or like in the previous slide when it was a binder clip and a bulldozer. Does it have anything to do with the complexity of the items as well?
Well, I will get into that in terms of my actual study, in terms of the sort of details of the individual objects and the sharpness and features of the objects as well. And that's all controlled for in our study. Okay. I will say in terms of this example, it very well would have something to do with it. Things that are more out of focus are likely going to be slower as well, so that might contribute. I think this is mainly sort of an artifact of this specific example that it's sort of like the picture is focused on the cat and everything is sort of blurred in the background. But that's not necessarily the case when you're engaging with large and small objects in the real world. Okay. Yeah. So it's definitely a good question. There are many, many factors that would go into this as well. Essentially, I'm just trying to demonstrate that inferred real-world object size is one of these factors.
Cool.
Okay?
Yeah.
Yeah. Okay, so to test this question, partly to answer the question that was just raised, essentially what I did was to use line drawings of objects instead of actual images of objects. And the reason for this is because line drawings of these objects give a little more control over specific aspects of the object. So objects come with all sorts of what's called low-level information about the image. There's many features of objects, including color, including the luminance, including like object perspective and object depth. And taking just images of objects, sometimes these can be a little bit difficult to control for. But being able to select line drawings or draw specific line drawings for individual objects enables a little more control over some of these features, including the physical object size. I can draw all of the objects to be the exact same size or roughly the same size, as well as features like brightness or luminance and contrast. And so from these line drawings, you can see all of these line drawings. We have 30 objects in total. From the line drawings, two separate groups of sub-selected objects were constructed. Basically, the groups were divided into objects that are known to be small, basically objects that are handheld or smaller, and objects that are known to be large, so objects that in this case were body-sized or larger. This is a division that has been used before in the literature as well, in several papers, but essentially just trying to construct two groups of separately sized objects. However, you can see that they're all physically the same size, and that will be consistent throughout the experiments that I'll demonstrate. Okay, so we now have a set of small and large objects, and what I did for the experiment was to construct an experiment in which either a small object or a large object was presented on the screen by itself. Objects could either be presented horizontally or vertically. For the purposes of the slideshow, I'm just going to show the vertical objects. And so again, small or large objects would be presented. And then following that, a single attentional cue would be presented. Basically, this cue is just to attract your attention to one specific location on the object, in this case, either on the top or on the bottom of the object. And this is just to give attention essentially a starting point for where you're going to be attracted to, and that will come into play shortly. Following the cue, there was a brief interval where the participant was just observing the object on its own. And then eventually there was also a target, as well as a distractor that were presented on the object, one on top, one on the bottom. The targets were T's or L's. The participant just had to say whether they saw a T or an L in a given target, in a given object. The distractor was what's called a TL hybrid. So basically it's essentially just a T and an L that are stuck on top of one another. And so that's distracting because it's a similar sort of shape to the target. And essentially the target could either appear in what's called the cue valid location, so in the same location as the cue, so where your attention already should be, or alternatively, it can be presented in the cue invalid location. That's the location opposite from the cue. And the reason this is important is because it allows us to measure what's called an attentional shift. So an attentional shift is how long it takes a participant to shift their attention or move their attention from the location where their attention already is, the valid location, across the object to the location where the target might be if it's in the invalid location. And that shift would take some time that we can measure. And finally, there's just a fixation that takes some time in between trials, and participants would be presented with a new object and do this all over again. Following the experiment, participants were also presented with this post-experiment size assessment. They weren't told anything about the objects beforehand, but basically in the size assessment, they viewed each object one at a time, and participants were asked to rate how large or small they thought the objects were on a scale of 1 to 6, 1 being the smallest, 6 being the largest. The reason we do this is we can then take the object size ratings from each participant and use those ratings in a regression with the response times. We can basically use the sizes of the objects that participants thought they saw and try to predict how fast or slow they responded to each object on a participant by participant level. In this case, a participant might respond that they thought a pool table was about 5 out of 6 on the size rating. So to start, I will talk about the first experiment in which we used what's called a spatially predictive cue. So if I can call your attention back to the paradigm that I just demonstrated, essentially what this would mean is that the cue, or the red bracket appearing on an object, was more than likely to predict the location of the target. In this case, targets appeared 75% of the time in the same location as the cue, and only 25% in the invalid location. The reason to do this is that if it's spatially informative, essentially the invalid location is going to be less likely, and participants will take longer, and the time it takes to move to the invalid location should potentially be longer. But anyway, getting back to the question, specifically, is attention more diffuse within these large real-world objects compared to the small objects? Do we see a slowing of attention within objects that are known to be large compared to objects that are known to be small? Under these conditions, what we observed is the expected spatial validity effect, that essentially a cue valid location attracts attention very strongly, and it's much faster than in the invalid location. You can see on the x-axis is valid and invalid, that's the validity condition. On the y-axis, you can see its response time, that's how long a participant took to respond to a target. And again, we observe this expected spatial validity effect. But interestingly, what we also observe are essentially effects of object size. So in both conditions, valid and invalid, what we see is that it does, in fact, take participants longer to respond to targets in larger objects. And this is the size-based effect that I was referring to before. And this is interesting because it's the first observation that, in fact, attention is constrained not just by retinal size or how large the object appears on your eyeball, but also by how large you know the object to truly be. Now, interestingly, if I can again draw your attention back to the post-experiment survey where participants rated the size of each object, again, like I said, we were using these data points to try to predict on a participant level whether targets were faster, targets were responded to faster in smaller objects and slower in larger objects. And so this is exactly what we observed. So if you look on the x-axis, you can see on an object-by-object level that the size rating is represented from 1 to 6. This is averaged across all participants. And on the y-axis, you can see this is response time again. And what we're showing here is that, in fact, as objects are rated or known to be larger and larger, the response time actually slows down. And this was significantly predictive of the correlation between size rating and response time. Additionally, what we see is when we conduct a median split between large and small objects, or objects that are rated to be large and small, it actually perfectly predicts our previous groupings that we assumed were small and large. So all of the objects that we rated as small before the experiment, participants rated as small. These are represented in blue. All of the objects that we, prior to the experiment, rated as large were also rated by the participants to be large. This is shown in yellow. Additionally, on this median split, where we split the objects between small and large, there was also a significant prediction within the large objects as well. So as large objects became larger, the response time slowed down as well. So not only is there this size effect, but what we're also showing here is that there's a direct relationship between the relative object size and attention. Basically, as you know the object to be larger, the time it takes attention to be allocated within these objects actually slows down. So moving into experiment 2, this is essentially the same experiment, but what we did here was to reduce the spatial predictability of the cue. Essentially, to make this spatial predictability of the cue lower down to 50% valid rather than 75% valid. The reason to do this is that when you have a 75% valid cue, essentially there's some top-down predictability, there's some knowledge about where a target should occur. And so essentially what we're testing here is, does this top-down knowledge of size effect, does the top-down effect, does this knowledge of inferred object size that constrains attention sort of ride along with this top-down spatial predictability? And when we reduce the spatial predictability and only have the bottom-up potential cue, is this size effect still present? Again, on the x-axis, you see, on the left side, you can see valid and invalid conditions. On the y-axis, again, is response time. And what we see for experiment 2 is that under 50% of valid conditions, essentially we see the same exact effect. We do see a reduced validity effect. That's expected because, again, the spatial validity of the cue was reduced. But again, we still see that responses to large objects are slower than responses to within small objects. And again, using the post-experiment survey, we also see a significant prediction of the response time according to object size. So again, as objects become larger, response time slows down. Okay. Next, what we did was to, if object size knowledge contributes to attention, then what we should be able to do is that if we systematically reduce how identifiable an object is, we should then be able to essentially parametrically reduce the contribution of object size. So if you know that an object is a small object because you can identify it as, say, a domino, then you're going to have this size effect where you'll be faster to respond in the domino. But if we reduce how much you know about the object, how identifiable the object is, how much contribution of object size there is, then this contribution of object size to attention should therefore diminish. And so in order to test this, the next step is to essentially try to reduce this object identifiability, and to do this, each of the objects was scrambled. So right now what you can see on the screen is essentially what was called the no scramble condition. This is essentially just experiment 1A. This is a 75% valid condition. And what you see on this figure here, you can see no scramble retinotopic and full scramble on the x-axis, and what's called the difference in RT, or essentially the large minus small. This is the size effect on the y-axis. These are predicted effects. But essentially we know that this no scramble condition was significant. There was a size effect when object identity was known. So again, here's the original object. However, if we scramble the object using a technique that we call the retinotopic scrambling, here what we did was to essentially try to preserve the pixel location of all of the black pixels and all of the gray pixels, but then scramble them all across objects. So essentially, black pixels from one object were contributing to a black pixel location in another object, essentially to try to preserve object identity to a degree, but not completely reduce it. What we should see, most of you can still probably tell that this is roughly a domino, but you would agree that it's not quite as clear as previously observed. And so what we should see is that there would be this slight decrease in this effective size. Next, what we can do is to do what's called a full scramble, where we just completely break down the identity of the object, but still preserve essentially the boundaries of the object. So it's still roughly a rectangle, in this case for the domino. What we should see then is that as the object identity is completely broken down, you can no longer really tell what it is, then there should be no contribution of object size, because you don't know how large or small the object would be. And so in doing this, this is actually exactly what we observed. So in the no scramble condition, we found that there was a size effect of roughly 14 milliseconds, about 15 milliseconds. And then following that, in the retinotopic scramble condition, where we did scramble the object but didn't completely reduce the identity, there's now an effect that's roughly 8 milliseconds, and this was a significant difference between these two conditions. Finally, in the full scramble condition, where the objects were completely scrambled, the object size effect was completely reduced. There's no effective size whatsoever, all the way down to 0. So what we're now demonstrating is that essentially a reduction in object size knowledge and your ability to know how large or small an object is based on its identity completely diminishes how much object size affects attention. And so we're now demonstrating control over this size effect. However, there's some additional concerns as well. So there's also this potential that we might be able to modulate how fast an object is attended, how fast attentional shifts are, how much of attentional shifts are affected across an object. So how long does it take you to shift attention from one side to the other? We didn't observe this. We found essentially a general effective size, regardless of validity location. So in experiment 3, what we did was to essentially increase task difficulty in order to see whether this modulated the size effect. So as attentional demand is increased, when you really need to focus on specific locations because the task is difficult, does this also shape the effect of size? And so here, what we did was to just essentially use the same exact paradigm, but what we did was to change the targets. So no longer were we presenting T's and L's to participants, but now we were presenting what was essentially called a Gabor filter. This is just a circle consisting of a set of oriented lines, and those lines and the targets were either oriented 45 degrees to the left or 45 degrees to the right. And they would just respond to the orientation of the target. Now, interestingly, what we did was to manipulate the spatial frequency of the targets. So they were either four cycles per degree. Essentially, the lines were not very tightly packed. They were pretty thick lines, and it was easy to determine the orientation. Or what we did was to present targets that were what was called 8 cycles per degree. They were very densely packed, very sort of thin lines, hard to tell the orientation unless you were looking right at the target. So this is essentially the modulation of task difficulty. The 8 cycle per degree condition was much more difficult. And distractors were then a checkerboard pattern rather than these Gabor filters. So the task was essentially the same with the exception of the targets. And for the purposes of the slide, I'm basically going to just show the difficult the effects for the difficult targets. I do have a slide consisting of both, if anyone would like to see them at the end. But what we found was in the 8 cycle per degree targets, on the x-axis again is validity condition, y-axis is the response time. What we see is that essentially we still see a size effect, but in this case, the object size is actually modulating the attentional shift. What you can see is that when participants moved from the valid to the invalid location in large objects, there was actually a slower shift of attention, basically indicated by the slowing in the invalid condition, but not in the valid condition, in large objects compared to small objects. So not only does object size affect essentially how slow in general you are to attend to and within an object, according to whether it's small or large, but also according to how difficult the task is, how engaged attention is. In this case, it also modulates attentional shifts. And for the 8 cycle per degree, the high attentional demand condition, in this case, on the x-axis is the size rating, on the y-axis is the shifting cost, or basically the valid condition, or sorry, invalid condition minus the valid condition. What you can see is that there was a significant prediction of the shifting cost. So essentially, again, as you knew the object to be larger, the cost to shift attention between one location and the other was larger, so it took participants longer to do this. And so generally, again, what we've demonstrated here is that object size constrains attentional allocation, and it does so such that targets are identified faster in small than in large objects. And in fact, your knowledge of real-world object size predicts how fast you respond in this scaling fashion. So we call this size-based attentional scaling. You can think of this essentially as your mental representation of an object is warped, essentially, not just according to the physical size of an object, but it's also warped by the top-down knowledge, these inferred knowledge that you bring about an object size in the real world. And this warped mental representation of object size actually affects your behavior, it affects your attention, it has behavioral consequence. And then when we reduce the information about object identity, this systematic decrease in knowledge of object identity decreases this effect of object size parametrically. And so essentially just attention operates on real-world size rather than purely retinal size. And so this is sort of how you can think of your object representations when you're attending to, say, a cat and a man in the real world. So with that, I'd like to thank my lab. In particular, I'd like to thank my advisor, Dr. Shara Shamstein, and I'd like to thank Paul and Joe, who both worked on this project with me. So thanks, guys. And thank you all for your attention.
Yeah. I have a question. So first question, if we set the arbitrary reference for you, is it like object smaller than box will be small, and object bigger than this box will be like so I mean the naming. If we observe the naming, can you expect the result to be different, or the result? So I'm wondering whether really solely because of the object size, knowledge of the real world object size. I'm wondering whether it's possible relative knowledge of relative object size.
Well, I think this is a good question. Oh, I'm getting a lot of feedback, sorry. I think this is a great question. I do think it's very important to have demonstrated this essentially systematic prediction of the response time according to the participants' object size ratings. I think this gets to your question about this sort of arbitrary cutoff, because if it's just according to, this arbitrary set point about where you define large and small objects, then I don't know if we would essentially get this prediction, this systematic prediction of the slowing of response times according to participants' ratings, right? It would sort of just be this artificial break between the two groups. But I think this opens up a set of other questions that I think are really important questions. So some things that we've considered for potential future projects are, well, you know, what if you present participants with the same object identity, but you tell them, okay, well, this object is a toy instead of an actual large object. So you can imagine a scenario where you might have like a Tonka truck bulldozer and an actual bulldozer image. So it's just this knowledge that, well, that's a toy object. Would you expect it to be faster? I don't know. I think that's a great question, and it's one that's worth pursuing.
I have this with the relative size because I don't know, just for the example that the government of the it seems that the actual size of the robot might be might be smaller than what you were presenting, and the door or whatever the large object is the actual size is larger than the stimuli. So I don't know if this distortion or if this difference is between the knowledge of the object size you know and the size of the stimuli on the screen was the one that's driving feedback.
So essentially, is it just the fact that they're essentially distorted, or is it that the participants know that there's a size difference? I think they're sort of tied together. Essentially, we wanted to distort them to be all essentially the same size in the screen, so we could control for this retinal size. But I think it does open up potentially another question. Like, you know, one way that we could potentially study this is to take the distortion even further, right? You know, potentially what we could do is we could present these on a really large screen and present really large images. So the large objects were closer to their real size and the small objects were really large or something like that, and see if the effect still holds. I have a suspicion that that is not what's contributing to this effect, but I think it's a relevant avenue to pursue. Again, the intention was to control the retinal size and essentially measure the participants' knowledge of the inferred size of the object by using the post-experiment survey to serve as a predictive measure. But thanks for the question. I think it's a great avenue to explore.
Just curious,
Sorry, do you mind asking again?
do you see any individual differences?
In terms of the response time, I haven't specifically analyzed for, like done a specific individual difference analysis. I mean, there is variability within each subject, but I haven't done a full analysis to check whether, you know, some participants are just much less, have a much smaller size response. I'm not sure.
Okay. Another clarification and then follow up. You said your stimuli could be presented either horizontal or vertical, correct?
Yes.
So did you notice any sort of like congruency or effects of the orientation? Such that, for instance, like an envelope, I may have an orientation horizontal, whereas a door, I would expect vertical. You notice any effects?
Right. So I did not show the orientation analyses here just for simplicity, but I have done the orientation analyses, and when the paper is officially out soon, you'll be able to see them. There is no effective orientation on the size effect. That was a concern that we had, and also a concern in this case that a reviewer raised. So I think it's a great question, and there was no effective orientation.
I'm also curious whether, so let's say if you have the image set, the actual no size is 5. For example, for the entire trials, there are large items in the real world. For example, and do you expect to see some more sensitive difference in terms of their size, or do you just expect there will be no difference because the size is similarly?
If we just did the whole experiment with large objects, would we see a size effect? Essentially. Is that what you're asking? If we did the whole experiment with just large objects, or did the whole experiment with small objects, would this size effect be still observed, or would I expect? Right. So I think that the size effect might be potentially reduced, but given the predictive nature of the inferred object size, so if I can just bring this up again. Given that there's this predictive nature and we do the median split, there is an effect within the large objects. This is suggestive that we would still see a size effect. For instance, if we just presented the small objects. However, on the median split, there is no, it didn't reach significance, at least for the small objects. So in this case, there's no evidence to, whether I can talk about if that effect would still occur in the small objects. I think that's up for debate. I'm not sure. But potentially, given that just within the large objects, there is still this predictive size effect. So you might still observe a still graded response according to if you just did an artificial split in the large objects and say, these are all the small large objects and these are all the larger large objects. I don't know though.
So you're showing this effect of objects, but I think it would extend to scene samples. So maybe study a city scene with a bunch of streets shown, and then conversely showed maybe just one street would also do the side effect.
I think attention might be allocated or might operate differently within larger scene settings than in just an individual object. I do think, however, that this would have would hold consequence for scene perception and scene processing, given that potentially in a scene processing experiment, or when the way we think of processing scenes, you might think of treating each of the objects sort of equally because they're all just objects within a scene. But this is suggestive that in fact they're not all equivalent. They come with all this inferred knowledge about object identity, object size. I know there's plenty of work on semantics, and all of that contributes to and will shape your attention across the scene as you land on each individual object within the scene when you're looking at the scene. So I don't know essentially what would happen to attention to a large city or an individual street, but I do think that as you're looking at different objects within the scene, certainly this would affect scene processing.
I had a question, AJ, about just thinking about the mechanism for why we're seeing these differences in attention. You talked about the topography of the medial to lateral object size. Do you think that's actually the cause of why we're seeing these results, or do you think that's maybe a side effect and it's more to do with just the connections from prefrontal about inferred knowledge, something like that?
I think this is an open question. I think there's going to need to be more potential imaging studies investigating the ties between these attentional differences, whether we can observe a size effect in potentially attentional regions like IPS, right IPS in particular, and potential something like functional connectivity with regions within that cortical map observed by Conkle and Oliva.
Can you briefly just say what right
I don't know
IPS is?
I don't know the directionality. Sorry, keep going, Paul.
Can you just briefly say what right IPS is and does?
Right, so right IPS is a region, right intraparietal sulcus. It's a region in your parietal lobe that has been shown to be particularly involved in attention and in particular spatial attention. And so this task is essentially all spatial attention within objects. You're moving your attention between locations within an object. And so I would imagine IPS would be involved in that activity in this task. But I don't know if you'd be able to show an effect of inferred object size in terms of the IPS involvement here, or in terms of just attentional regions as a whole. I'm using IPS as an example. But does that answer your question, Paul?
Yeah, it does. Thanks.
I have a related question. I'm coming from psychology about with lesions due to stroke or who might experience object agnosia, like not being able to recognize or name objects. Wondering, of it, likely not the case, but are there like case studies or clinical studies implicating these sorts of networks or these sorts of regions? And again, not just the visual, like you're saying, topography, but other attention related or semantic knowledge regions.
So I don't know, especially anything sort of related to this size work, but I do know that there are certainly attentional deficits. Sorry, I'm getting a lot of feedback, Paul. Can everybody hear me?
Yeah.
Yes.
Okay, so I do know of specific demonstrable lesion experiments where people have shown if you have a lesion in, say, attentional regions, or specifically in like parietal lobe and IPS, that often people will show what's called hemispatial neglect, where if they have a lesion to one side of the brain in an attentional region, then they essentially can't attend to the side that's contralateral or on the opposite side of visual space as the lesioned region. It might be interesting to investigate something like, a size-based experiment using a lesion patient who has trouble attending to objects across, if you put an object essentially across their visual space, so moving from one side of the visual field to the other, and they have to essentially move across the object into the field where they can't attend to anymore. I don't really know what that would look like, but there are certainly effects of lesions on attention. That's definitely true.
I guess I'm thinking also, since there is this link with what you're showing, that it is on our knowledge about these objects to some extent. I would just be curious, patients who have lost the ability to accurately name objects, if these sorts of pathways are also involved, given the link to semantic knowledge.
Yeah, for sure, and I think that's definitely a great point. Like a visual agnostics or someone, for sure, if they don't know what the object is, I think that might certainly have an effect on this size effect. I'm not really certain, but I think it's certainly worth investigation.
Just to be respectful of everyone's time and the speaker's time, maybe we can pause the discussion here, but it can certainly continue on the online forum and continue from there. And for those of you who are here in person, please don't leave without signing that sign-in sheet so we can ensure we've got at least some kind of record of everyone being here.
If there are any more questions, I think it'd probably be good for our online listeners if we close everything down before we leave. So, we can sign off. Thank you, AJ, and Allison and the CCBVI student group for agreeing to work with us for our live audience and for our Allison.
I just want to clap.
Oh, okay. should we clap for AJ?
Yeah, thank you, AJ. Thank you so much.
Thanks, everyone. I do want to say quickly, if people have offline questions or still questions that I haven't answered, I'm happy to answer them by email or in some other way. But for sure, I'm open to more questions if there are any.
Awesome.
Thank you so much.
Thank you.
Okay, so to our sorry, I'm moving the mic so people can walk out of the room if they need to. Thank you, AJ, for your live presentation, Allison, CCBVI student group, for agreeing to work with us, our live audience, and of course our loyal online audience from across the nation joining us today. If you would like to be a future presenter of OnNeuro, you have a suggestion for a topic or article to discuss, or have any questions about our platform, feel free to send us an email to onneuro.com, visit our website, onneuro.com, and visit our contact section. You can leave your comments about the platform or visit us on Facebook and Twitter. Next month, we have Aditya Shukla, who is the owner of a psychological blog called Cognition Today. And this will not involve the CCBVI group, but we will hope you can still join. This has been a special edition of OnNeuro.